Hey folks, we're back and better than ever with another video for college algebra. This is section 4.1. We're talking about rational functions. And my dog is barking like a madman. Guy weighs 20 pounds. Somebody's walking by outside, maybe with a stroller, or maybe some old people going on a walk, and he's barking like crazy. Okay, order has been restored in the Vass house. Let's move on. Chapter 4 is about rational functions. It's a pretty short chapter, but there's a lot of information packed in it, so we're going to start with an introduction. Good place to begin our discussion would be, how about the definition of rational functions? Rational function is a polynomial function divided by another polynomial function, such as r of x equals p of x over q of x, where both p and q are polynomials. So we just got done with an entire chapter about polynomials. Now we're going to see what happens when we divide one polynomial by another. So the first example problem here, we're asked to write each equation in the form p of x divided by q of x, simplify, and then find the domain. So the first one is pretty easy. It's already written in that form and is already simplified for us. So this one, there's nothing for us to do here. It's already simplified. But we do have to find the domain. Remember, folks, we have a couple domain restrictions we've learned about so far in this course. One being can't take the square root of a negative number. Another one being that we cannot divide by 0. So we have this denominator down here. X plus 1 cannot equal 0, which means x cannot equal negative 1. So if we're to write that domain in interval notation, we would say we'd start by looking at the entire real number line and then just take out negative 1. It gives us that domain right there. Okay, so that one was pretty easy. Let's move on to the the next one here. By the way, that should be x plus 1 cannot equal. Okay, folks, pandemonium again. Got to go solve a problem. Hold on. All right, folks, I'm back. It's a good thing I have these large protective dogs because that was my neighbor pulling in his garage. He's lived across the street from me for 18 years. Good thing that my dogs are there to bark at him, make sure everything is safe and sound in the neighborhood. All right, so let's take a look at this part B here. We have g of x equals 2 minus this rational function, 3 divided by x plus 1. So we have to get this into the form p of x divided by q of x. Right now it's not in that form because we have 2 minus a rational function. So what we need to do is get a common denominator here. And I'm going to multiply the value of 2 by x plus 1 over x plus 1. So this is going to become 2 times x plus 1 over x plus 1. It's equivalent to 1, so I'm not changing the value of 2. And then I'm going to subtract 3 over the quantity x plus 1. All right, so what is that going to equal once we go through that? It's going to be 2x plus 2 minus 3 all over x plus 1. And that equals 2x plus 2 minus 3. It's going to be 2x minus 1 over x plus 1. And that's my simplified function for g. Okay, we still have a domain restriction we have to be concerned with. So let's take a look at that denominator. X plus 1 cannot equal 0. That gives us the same domain restriction we had before. X cannot equal negative 1. So we're going to have the same domain as we did in the previous function. All right, so far this is pretty simple. Let's move on to C. So in example C, things get a little bit trickier. We have one rational function, 2x squared minus 1 over x squared minus 1, and we are subtracting another rational function, 3x squared minus 2. We already have a common denominator, so we don't have to work on our denominator. All we have to do is combine like terms in our numerator. Let's be careful with this, though, because we are subtracting the entire quantity 3x minus 2. So that will be 2x squared minus 1 minus 3x minus negative 2, which turns into a plus 2, all divided by x squared minus 1. So let's go do some simplifying on that numerator. H of x is going to be 2x squared minus 3x plus 1, all divided by the quantity x squared minus 1. And this is our simplified function, rational function for h of x. Now I need to look and see if there are any domain restrictions. Well, there is something about this one that we need to be aware of. Both the numerator and denominator are factorable. So for the numerator, I'm looking for factors of 2 that add up to 3. That would be, let me see, that's going to be -2 and -1. So this is going to factor into 2x minus 1 times the quantity x minus 1. If you're not sure how to do that, I've done enough of these. I can kind of go through that really quickly. Go back and look at the diamond factoring method resource that I provided to you a couple chapters ago if you still need help factoring something like 2x squared minus 3x plus 1. All right, the denominator is a difference between two squares. So that factors into x plus 1 and x minus 1. So hey, take a look at what we have here. We actually have some terms here that cancel out. So I have x minus 1. I have x minus 1 that cancels with x minus 1. So really what I should say here is h of x is not equal to what I had before. I can simplify it further and I can say h of x equals 2x minus 1 over x plus 1. Okay, and that function is starting to look familiar. That's what we had in the first example. So this thing here that was kind of crazy looking simplified down to what we had in the first example, and same thing we had in the second example. So far this is getting pretty, this is kind of a little bit repetitive. Let's talk about the domain restriction though. We still have x cannot equal -1 because that would make my domain equal to 0. But don't forget about this factor. Even though we crossed it out because it canceled with 1 in the numerator, x cannot equal +1. Look back at the original function. If you plug in +1 there, it's going to give you a 0 in your denominator. So this domain restriction is a little bit different than the previous one. We're going to remove -1, and then we're going to remove +1 from the real number line, and we're left with that as our domain. Okay, so far so good. Let's move on. One more example here. This is frightening. We're dividing two rational functions. So I don't personally like dividing fractions. I'd rather think of it as a multiplication problem. So what I'm going to do is I'm going to take this and rewrite it as 2x squared minus 1 over x squared minus 1. And I'm going to multiply by the reciprocal of the second one, which is x squared minus 1 divided by 3x minus 2. Well, there's some nice things that happen there. I have this x squared minus 1 here and here, numerator and denominator, those cancel. So what I'm left with now is r of x equals 2x squared minus 1 divided by 3x minus 2. And that's as simplified as we can get that. There's nothing there that would cancel out. But I have to consider now my domain restriction. I had an original denominator here. In fact, we had it here and here. That original denominator had x squared minus 1. So I know x squared minus 1 cannot equal 0. That tells me that x cannot equal plus or minus 1. But also notice here, if this piece right here, 3x minus 2 over x squared minus 1, if this equals 0, it is in the denominator of this division problem. This piece right here, let me go ahead and highlight, this piece right here only equals 0 if 3x minus 2 equals 0. So I need to say, hey, 3x minus 2 also cannot equal 0. That tells me that x cannot equal 2/3. So I have three different values I have to remove from the real number line. -1, +2/3, and +1. That's going to look like this in interval notation. All right, there you have it, folks. There is the domain for r of x, which simplifies down to 2x squared minus 1 divided by the quantity 3x minus 2. Let's move on to example 2. Example 2 here says, consider the graph of the rational function 2x minus 1 over the quantity x plus 1. And that's the function that we've seen show up in several different formats from the previous examples. I'm asked the following. How does the graph behave as x approaches -1 from the left? Well, let's go up. Let's first take a look at this graph. Okay, so we're asked here to consider the graph of f of x equals 2x minus 1 over x plus 1. So let's go ahead and graph it. It's hard to consider the graph without looking at it. So we're going to graph a rational function here. And our numerator is 2x minus 1. And our denominator is x plus 1. So we grip it and rip it and bang, there we get that graph right there. So we're asked some questions about that graph. Take a mental picture of that. All right, so let's take a look back at the questions we were asked about this graph. Here we go. So how does the graph behave as x approaches -1 from the left? All right, so I've added the vertical line x equals -1. As we approach that line from the left, the function goes off towards infinity. So this is how we're going to document that. As x approaches -1 from the left, f of x approaches infinity. Okay. Now the rest of these questions, I am going to look at the graph and answer them. I want you to just double check and make sure you can understand the interpretations I've made of the graph. All right, so we've captured some observations about the graph here. We have how it behaves around this domain restrictions of x equals -1, and then we also have what we call the end behavior of the function. And end behavior of the function is what happens as x goes off towards infinity and off towards -infinity. If you remember from our chapter about polynomials, the behavior was, if it was a polynomial, we knew what the behavior was. It was either going off at one end towards infinity and the other end towards -infinity, or both ends were going off in the same direction, depending on whether or not the degree of the polynomial was odd or even. Okay, enough about that. Now let's go back and look at the graph and make sure we understand some of these things. So as x approaches -1 from the right, that means I'm coming in from the positive side. You can see that the graph goes down towards -infinity, which is where I get this value right here. As x approaches -1 from the right, f of x goes towards -infinity. Now let's talk about this end behavior. So hopefully in the graph you can see this. Not that. You don't need that. Hopefully you can see this. I'm going to graph another function. I'm just going to graph, let's try this. Menu, graph a function. I'm going to graph just y equals 2. Oh, take a look at that. So as x goes towards positive infinity, the blue function graph, the rational function, approaches this y equals 2 line. As x goes towards -infinity, the graph still approaches that y equals 2 line. So that's kind of interesting. All right, let's look back at the notes here and see what we have next. Based on your analysis of the graph of f of x, complete the definitions for each type of asymptote. Well, the first one here, the line x equals c, is a vertical asymptote of f of x if, as x approaches c from the left or as x approaches c from the right, f of x approaches infinity or -infinity. So that's what gives us a vertical asymptote if the graph goes off towards infinity in the y direction. Now let's talk about horizontal asymptote. The line y equals c is a horizontal asymptote of f of x if, as x goes off towards infinity or x goes towards -infinity, f of x goes towards c, where c is the y coordinate of our horizontal line. Okay, so folks, that's an example of vertical and horizontal asymptotes. And the reason I asked you to graph this function 2x minus 1 over x plus 1 is because you can see both. You can see that the graph approaches a horizontal asymptote in both directions, and there also is a vertical asymptote. Okay, so back to the notes here. Question 3 says sketch the graph from h of x the graph of h of x from example 1c. Feel free to use your calculator. So I got to scroll back up and take a look at that example 1c. So it was this one. I'm going to graph the unsimplified version of this right here. 2x squared minus 3x plus 1 over x squared minus 1. Alright, so let's go ahead and just start a new document here. I don't need to save that one. And we are going to graph a rational function. This little key on my Inspired just gives me that fraction bar. So we're going to go 2x squared minus 3x plus 1. And we're going to divide by x squared minus 1. Now, if you recall from the last example we did, when we in example 1 part C, when we simplified this function, it was the same one we had graphed before. Okay, and this should look familiar because we already have a graph that looks like this. Okay, but what is different about this one? Well, if you recall, this one had a domain restriction of +1 and -1. So I can see the domain restriction of -1. That's this vertical asymptote. But I wonder what's happening here at x equals 1. I can't see anything in the graph right now. So what I'm going to do is I'm going to go look at a table of values. I can do that on my calculator by going Menu, Table, and Split Screen Table. Oh, well, look at that. Look at x equals 1. The function is undefined. That's because 1 is not in the domain of our function. So to the left of x equals 1 and to the right, the function is defined, but right at x equals 1, it's undefined. So how are we going to represent that when we try to graph this thing? Well, I don't know. Let's take a look. First thing I know is that I'm going to add some lines to this graph. I'm going to go ahead here and I'm going to mark my vertical asymptote of x equals -1, my horizontal asymptote of y equals 2. And then I'm going to go ahead and graph the function. Okay, we know that this left-hand piece looked like this, and the right-hand piece looked like this. But that's not exactly correct. Okay, and so I'm going to get rid of that. The reason it's not exactly correct is because at x equals 1, it's undefined. So what I have to do is I have to represent that at x equals 1, there's actually a hole there. Let me just double check my graph. Oh, at x equals 1, that should be above the x-axis. I have a y-intercept of -1. So I didn't do a very good job of sketching that graph. I should really fix that. So it looks like I go through this point, and then I have a hole right here. So my graph really looks more like that. That is a good sketch of the function h of x from our previous example. Okay, folks, we're done with page 1 here. Stay tuned in a couple minutes for page 2.